Yeah, so I'm going to talk, well, my talk is titled for AGI, minimal embodiment is all you need, but you need it all. So I'm going to argue that we need a really minimal form of embodiment if we want to move towards AGI, but that minimal embodiment is incredibly important, and it's important not to miss the lessons from embodied intelligence if you want to create such things. And for those in the audience who don't know, AGI means animal level general intelligence. At least that's what it's going to mean in this talk. So I'm going to start by looking at the sort of space of possible minds, or the space of possible general intelligences, and trying to abstract away from all of them and see what's core to them all. So obviously we have things like humans with their own particular type of embodiment. We have things like octopuses that we've already seen multiple references to with a very different type of embodiment, very different type of actions that they can do in the world. We also have things like perhaps alien slugs that might be general intelligences that might see or perceive the world in a completely different way. And of course, we have AI systems. And by this robot, I want to also represent both actual robots, but also AI systems that might exist in very abstract spaces. So for example, existing online, crawling through the internet, looking for data like that. So there might be very, very different things between all these different types of possible minds or possible intelligences. And the one thing I think that they all do have in common is that they can do goal-directed action in an independently involving environment. That's the thing that ties them all together. But the ways that they do that is very, very different between all of them. And now, so taking that abstract core in the center, I want to build back up from there towards a more embodied intelligence view of what it means to be able to create some kind of general intelligence. And just relating this back to the introduction today, taking this sort of simplified version of this well-known example, we have embodied intelligence on one side, and it's doing something different to old-fashioned AI, where they sort of miss out this part in the middle that seems clearly important. And in fact, it's hard to think now how things would work without that bit in the middle. If you abstract away from all the different types of morphology, different types of embodiment you could have, where do you end up on this divide? And I want to argue today that when you abstract away and you just get to the core elements of an agent interacting with the world, you don't move anywhere towards the old-fashioned AI side. You just get something on top of the embodied intelligence side, even with very, very minimal embodiment. So to do this, I'm going to start from a starting point I really like from one of Andy's papers, where he says the task of a brain when viewed from a certain distance can seem impossible. It must discover information about the likely causes of impinging signals without any form of direct access to their source. And he builds up from here the story of how an agent might do this. So if you imagine a baby getting bombarded by sensory information, it looks something like noise. It's just moving around, and like it's hard to distinguish any patterns in it at all. But there are some tools it can use that it has in its arsenal, and one key tool is interaction. So you may see there's a cursor on the screen. When that clicks, there's a part of that noise that's changing at a slightly different frequency, that if you're actually doing the clicking yourself, you might start to notice and pick it out easier because that part of the noise moves towards where you click on the screen. And I have a bunch of little very informal experiments that you can find on my website that do this, sort of allow you to do interactions with noise and see if the patterns in the noise appear quicker if you do such interactions. But for one that we can do now, assuming it works over Zoom, here's a very bistable illusion. It should look like it's rotating clockwise and then counterclockwise and sort of flipping between the two. And my point is that interaction is the key thing, and it's your actions that change what it is you actually perceive and how you model what is going on here. So if you literally put your hands out like you're driving a car and you're holding this like a steering wheel, and then move your hands to the right or to the left, you should find, just doing this in front of your screen now, that it moves in relation to how you move your hands. And in fact, you don't need to do something quite as exaggerated as that. If you just take your head and just tilt your head slightly left and right, you should probably find that that also changes what you see and changes the way that this is rotating. And the point here is just that it is the interaction with our environment that we are modeling, and the actions and how we can interact with things that are playing a very key role. And on the slide is some actual real work in this area, and not just the little silly informal experiment. So I work in the area of more of deep reinforcement learning. And the question I want to ask is, how can you go from an agent that starts just basically perceiving noise and turn it into something that's seeing an environment with lots of different objects with different rich possibilities for interaction? I don't know how to build that myself. I think that's going to take huge teams of people with lots of money to be able to solve, but I do know how to build an environment that can encourage people to try and build these kind of agents. So that's what we did. This is the environment. In the middle, you see goal objects. On the right, you see different objects that you can interact with. And the key point here is that it's very, very, very simple. The agent is just that little blue sphere at the bottom. But even in an environment like this, the fact that it can bump into things and push them around allows you to set up many different types of cognitive tasks. And even this agent has internal states. It needs to know its velocity. It needs to know how much time is left to complete an episode, and it needs to solve some of the cognitive tasks. It needs memory. It needs to remember previous things that it's seen. So even in this kind of very abstract deep reinforcement learning setting, like very far away from actual robots in the real world, you still get some key elements of embodiment. So we built this, and there's tons of different tasks, all taken from animal cognition literature, or at least inspired by, that can look for different cognitive abilities of such agents. And we set this up as a competition to see how well AI agents can do at solving these kind of tasks. And as you saw in the plenary lecture this morning, AI systems, like for example, the one in Sequest in the link, they have certain things that they can't do very well. And those certain things, we believe, are solving these kind of tasks. So for example, here's showing how they link to animal tasks, and you're seeing a version with animals and a similar task with agents. And you'll see on the right-hand side, even the fail cases, so where some animals fail to understand that they can move around this transparent object to get to the goal, the food that they want, are recreated in AI agents. And you actually see very similar fail conditions, just bumping into the thing. It looks like going forwards towards it is the correct thing to do. And here's an example of comparing the winner of our competition with a child. So we tested children aged 6 to 10. This is one of the children, I don't know which age, anonymized, taken from that data set. So I'm going to play the one on the left. And they seem to have worked out that this object can be used as a tool to pull that green food off the red zone, which they would die or end the episode if they go onto, and almost immediately worked it out. And on the other side, you'll see the other one of the two. And it should probably be immediately obvious that the child was the first one that immediately understood the affordances in the environment and what it could do with the objects after having some previous interaction with the environment, but never seeing a test like this before. And on the right side, we have an AI agent, and that was the best one in our competition. It did some very impressive stuff on simpler problems, but there's just no chance of solving a problem like this. If you want to look more into this, you can play all these tests yourself, just online in your web browser at animalaiolympics.com. And you can also watch all the agents from our competition, see how well they did on all our 900 different tests. And I also want to say that this kind of environment is also a playground for lots of different alternative approaches that are trying to bring in more important ideas about what it is to be an agent interacting with its environment. So for example, this work, we have a deep active inference agent that's learning a subjective timescale model. And what it's doing is basically every time the expected free energy spikes, it records that in its memory, and it learns transitions between these spikes. So it learns the transitions between two different surprising states, and that allows it to look really far ahead in time and only see the interesting things. So for example, in the bottom left, you can see if I put it facing the wall, then the STM, the subjective timescale model, thinks, oh, I really need to turn around, because what it expects to see when it turns around is interesting things. Even if the environment's empty, it thinks it might see something interesting. So you get an agent that's really incentivized to explore. Whereas compared to the normal approach, you just get an agent that's sort of fairly can only unroll things one by one. So it's very slow how it can think ahead and can't like take these leaps forward. But the long-term goal, of course, is not to like live inside this little impoverished simulated environment. And we want to be able to build robots that can solve problems like this Aesop's Fable task, where the corvid has to drop the rock on the left-hand side into the water, let the water rise until it can reach the food. But obviously, this is a huge challenge for robotics. Like you need to detect the food, detect that there's open tops on the containers, these translucent containers that are hard to see in different lighting conditions. You need to notice there's different substances and that they have different properties. You need to detect that there's objects around that could help you to successfully grip these irregularly shaped objects. And you have to do all that before you even solve the cognitive problem, which is understanding water displacement and learning that you can use that to get the food. And we want to solve this in a setting where the robot has never seen this type of problem before. It hasn't been designed just to solve this problem. It's been designed to explore it and interact with environments. And then when faced with this problem, it explores around and eventually learns how to solve it. So incredibly hard long-term goal. But in the short term, under final negotiations, we have a DARPA-funded project called Recog AI, which is going to go into a lot more detail about the stuff I've already presented. And hopefully very, very soon, we'll be hiring 2 postdocs for 2-year positions. So if anyone here is interested, please get in contact, and looking to basically expand everything I've talked about today into bigger and better versions of what we have. So finally, I just want to leave you with a quick famous koan from the Zen world. So we have 3 monks sat around staring at a flag, and the first monk says, I see the flag, it is moving. The second monk, more experienced, says to the first, well, no. What you see is the wind that is moving. Third monk, more experienced than the other 2, comes along and says, oh, you're both fools. It is the mind that is moving. And at this point in the story, usually Mumon comes out and tells them they're all idiots and this is not the path to the Enlightenment and they're all wrong. But maybe we can add like a different ending to this story, and we can have perhaps someone in a nice, colorful shirt turns up and says, it is affordances that are moving. I don't like the term affordances. I just needed a 1-word thing to fit this. I think maybe something like the inseparable unity of brain, body, and environment is dancing its dance to the tune of predictive engagement and interaction is a much better way of putting it, but a bit less memorable maybe. So yeah, that's everything I want to say. Thank you for the time.
Okay, thank you very much, Matt. It's a lot of content in 10 minutes, but I think we got all the message from you. Yeah, thank you.